Hi, I'm Chris DeLeon. This is a video I'm preparing for both review by students taking LMC 6310 at Georgia Tech in the Digital Media Masters program, as well as people outside of Georgia Tech who are interested in learning some introductory processing. This is the content of the first lab or two, at least is what I'm covering for now. And if you're not familiar with what processing is, you can get it for free at processing.org. It's built originally by MIT's Media Lab, and basically it's a container for writing Java code for real-time interactive applications. Now, my personal area of background and interest is in video games, but processing is used all the time for non-video game research applications and prototypes and interface demonstrations as well, and graphics programming. It's not just for game use, although, as I'm going to demonstrate, it certainly can be used for that. So you'll go to processing.org, download processing. Since you don't even know really what it is you're getting into, maybe don't feel obliged to give a donation at this time. But keep in mind that if you make $1 million bajillion dollars, you should give some back to the Processing Foundation. Download, and you're going to want the latest version. It's supported on Windows, Linux, and Mac, so no matter which your operating system, you should be in good shape to use it. 64 and 32-bit respectively. If you're not sure, I'm going to bet 32 is probably going to work fine for either. It'll only take a moment to download. It might be a couple hundred megs or less. You can actually just unzip the file in the same directory that it's in and then run the processing application. It's not something you need to run an install program or configuration or anything like that. And once you open it up, you'll get a blank window that looks something like this. Now, before we get into what we can do with processing, I want to clarify that some people, when they've become familiar with it, or they've only seen demonstrations with it, become worried that it can't be used to make anything besides kind of some basic graphical demonstrations. And so this was, when I was coming into writing processing code, my question too. And so I wondered, could I use it to write a basic platformer example? And so here, this goes beyond the scope of what we'll be covering in the class. But it's evidence that we can make a scrolling camera, have collectible power-ups. When the character touches a red block, everything resets. You see we have a timer, have some outline text, playing music and making sound effects. There's really enough here to make a basic demonstration about how to write certain kinds of code, how to prepare a certain type of engine, and how to handle collision detection for that kind of environment. If you're interested in more about that kind of example, provide the source code to it on my side site, which again, for the most part, will not be calling much attention to my outside material, but for the first point, I want to call attention to if you're maybe more advanced than what I'm covering here, which will be some introductory graphical coordinates and programming practices. You can check out the code for that kind of demonstration at this URL, hobbygamedev.com/int, and if you look for the platformer game source and processing there, you'll find the full source code to it. Recently updated to work with the latest version of processing. Now likewise, that still looks pretty rough, like a crude demonstration, and so I prepared a more complicated example as well at hobbygamedev.com, int the making of A10 Thunderbolt 2. I'll leave that URL down here. And I just wanted to prove to people that processing really has a lot of room to grow and move. You can make some pretty sophisticated, complicated programs. So we have a little jet plane game. With all kinds of bombs and fire and smoke particle effects, weaponry, heat-seeking missiles. And destroyable terrain, of course, is a non-trivial thing to program. So this is also put together as a demonstration of how that works. Now, one thing about this class. So that's sort of a dumb, arcadey toy. It's not even a game, of course. There's not really a goal. There's not really an objective. Just something to play around with. But the nature of the course that these skills are being covered for focuses on computers and expressive medium. Some people sometimes wonder, what does that mean, expressive medium? Now, there's various interpretations. There's things you can program that are sort of like interactive poetry. There are things you can program that somehow communicate something about an experience in your life or something about something going on in the world. Could even be about how information is organized in a certain way to demonstrate a bias or to reflect, basically just using the computer as something more than a tool. But of course, pure entertainment's not really expressive in the same sense as maybe the class is about. And so as a simple illustration, I also wrote a variation of that, still available at that same URL, where I've added one line of text to the screen and a little bit of code to add some numbers for it. At the bottom here, you'll see the amount of taxes spent on this airplane for the fuel, for the machine gun rounds, for the smart bombs. And if you wreck the plane, the other $17.5 million. And the idea that you can start playing then unload $500,000 of arsenal instantaneously with a full load of the plane, gives you the idea that there's something more going on here. Suddenly it's critical. Suddenly it's political. Suddenly you're wondering about how else $500,000 could be spent on schools, on roads, on public safety, on public health care, just by adding one line of text to the screen. So again, both those examples are going beyond what we're going to have time to cover in the course, and in specific examples we're going to talk about, but I just wanted to show an upper bound for the kind of things that you can write these things in processing, and it's not gonna skip a beat. It'll totally keep up with you. Now for our first application we're going to write, inside here, we can do a little test and check out hello world. So by default in processing, unless we start adding functions, which I'm going to talk about functions in a moment, which are basically grouped chunks of code, until we start doing that, it's just going to run the code top to bottom, line by line. And right now we have only one line, which is saying to print line, the LN's for line, a string in quotes, hello world. This could be any words between the quotes. You could write your name, you could write a different message. These parentheses indicate that these are the argument that goes with this function call, print line. And a semicolon is how we're going to end basically all the lines in programming that don't open up a new brace. That has to do with, that's the computer's clue of where a line's supposed to end. And when I press play, it's going to create a little postage stamp size window, because we're not doing anything graphical yet, but you'll see down here in the console where it says hello world, that's our output. And this is one of the ways that we can actually export values when we're debugging in a processing application to see what a number currently is in memory, what a string is set to, as well as we can even just put out words like this to figure out when the code reaches certain points when we start writing more sophisticated programs that have code that hands off control of the different functions as it operates. Once we click and close this, oh, by the way, if you don't see that console, one thing that can happen in processing, at least in older versions, is that the window could be sized in such a way you might not see it. As long as the window's tall enough and you scroll down a bit, you should be able to see that console and not lose track of where you're at. Let's close that window. And now, most of the way we're going to start most of our processing applications, rather than doing this whole line-by-line thing, we'll go back to that when we revisit some of the basic structures in programming, is we're always going to have two functions that are kind of built into processing. Void setup and void draw. Setup gets called as soon as the program starts. So this is a place you can configure the screen's resolution. It's the place where you might set up where things are on the screen. Draw will be called repeatedly every single cycle of the program. And now, even though it's called draw, it's not just for drawing operations, like updating the graphics on the screen. It's also where you're going to be putting your frame-by-frame logic for how things will update as positions change during the interactor's involvement with the program. One of the most common calls that we're going to be seeing inside setup is size. Size takes two arguments, as an x value and a y value. I want to point out that the comma here is not to indicate 640,480. The comma is separating two separate values, 640, which will be the width of our window for the processing application, and 480, which is the height of that window. And when I press play, we get this window here. I'm actually going to shrink that a little bit further down, just so we can see. Let me do a quick measurement on my screen of what space we have to work with here. It looks like maybe 720 by 440 will be a good size. 720 by 440. And these can be any numbers, is part of what I want to call attention to. I just want a test window. Clicked it multiple times. Let's close the old ones. There we go. This way, when I run the test window, you'll be able to see it completely separate from the code, and we can point to different sections about what's happening in our demonstration. Now graphically, anything we put inside setup, again, will only happen once when the program starts. So we might say rect, and we can give this a few different numbers. Let's close our previous version of the sketch we launched. I'm going to say 30, 40, 50, 60, semicolon. And these four numbers are specifying the properties of a rectangle that we're going to draw once when the program starts. Because we're only doing it in setup, not in draw, it'll never be updated, it'll never change. When I press play, you'll now see this rectangle corresponding to 30, 40, 50, 60. And now take a close look at where the rectangle is, because when I change these numbers, 130, 140, 150, 160, and press play, we now have a different rectangle in a different spot. Now, what I want you to do, if you're following along this video, hopefully you've already installed processing or downloaded it, if you haven't yet, please do. It's going to be a lot more beneficial to follow along. Is I want you to pause the video and try experimenting with changing these 4 different numbers to see if you can figure out, without looking up the API documentation online, without searching the web, what do those 4 different numbers have to do with a rectangle being drawn? Can you figure out how to change the size of the rectangle along one axis or the other? Can you figure out how to control the position one way or the other? And so maybe as an exercise, can you make this so it starts 10 pixels from the edge and 10 pixels from the top and just 10 pixels short of the right side and 10 pixels short of the bottom side of the window that you're in? Give it a pause, play with those numbers, see if you can figure out what each of these 4 numbers corresponds to. Maybe change each one at a time. Stop to kill the application, play to try it again. And again, come back when you think you have a clue about them, and I'll kind of reveal how we do it. Are you still watching? Did you pause? Hope you paused. Okay, well, we're going to move on. I'm going to hope that you've paused and tried it. Now, to reveal the answer to these, the first number is how many pixels from the left side of the screen we're going to draw the rectangle. The second number is how many pixels from the top of the screen we're going to draw the edge of the rectangle. And the last pair of numbers, we can actually kind of look at these as 2 different pairs. It's an XY coordinate for the upper left corner of the rectangle, and the next 2 are the width and the height of that shape. And so if we want 10 pixels in from the side and 10 pixels from the top, now when I press play, you'll see this rectangle is 10 pixels from the left side and 10 pixels from the top. Now how would I figure out how wide it is to make it just short of the edge of the window by 10 pixels? Well, we set the size up here, so we already know it's going to be 720 minus 10 to account for the left margin, minus another 10 to make for the right margin, 700. Likewise, we can do the same trick for 440 pixels tall, and we know we have 10 pixels along the top edge and 10 pixels for the bottom edge, so minus 20, 700 by 420. When I press play, you can see now we have a border around the edge. Now, something to note about this is that if we change the dimensions of our window, if instead of 720 I make this 700, suddenly it doesn't line up anymore. You can see now it's going off the edge where that rectangle is, and it's safe to draw off the edge. It's a way we can experiment with it. Something we can do to make it more obvious to ourselves is we can actually write in place the math that we did, so we can notice that when this number changes, that number needs to change too. We had 10 for the left edge, 10 for the margin. Likewise up here we had 440 minus 10 for the edge, 10 for the margin. But this is still a little more complicated than it needs to be. This 720 processing automatically when we set the window size gives us variables called width and height that'll always be kept up to date with the numbers we set in size. So I'll press play. You'll see we have a 10 pixel margin around the edge. But if I change the width of my window from 720 to 680, sure enough, it's still following the edge of the window. And we have the same sort of issue of, okay, well, so we want the margin to be 10 pixels. What if we want the margin to be 20 pixels? And this is where we can start to declare variables to label our code. So we might say int margin equals 10. This is telling the computer to keep track of an integer, or int is short for integer. Remember, an integer is any number, positive, negative, or 0, that does not have a decimal point in it. So it's not 7.3, it's not negative 1.8, but it could be negative 10, 0, 5, 1,000, and so on. Margin is just our label that we're going to assign the number into. So when we reference the number in code, we're going to use the word margin. This word could be anything. It could be sheep, it could be maple syrup, it could be crazy bananas. As long as it's all one word with no spaces in it, that signifier means nothing to the program, only to us as a clue for how we mean to use it. And equals 10 here is telling us that next time we reference the word number or the label margin, it should be treated as the number 10. And we can change the value associated with it. We'll show you how to do that in a little bit. But so we can change this expression to replace these 10s with the word margin. And here we have these minus 10, minus 10. We could say minus margin, or minus 2 times margin. We'll do the same thing. You'll see we're going off the right side of the window. Now I could expand it a bit, and you'll see it because I'm over here. But another thing we can do is we can actually break the line to keep our code readable. And you'll see me doing this throughout as we work on longer and longer examples. White space in programming code, and this is true for Java, this is true for ActionScript 3 and C++, and a number of other programming languages that are pretty common. The white space isn't actually important to it. What I mean by white space is spacebar, enter key, tab, multiple spaces, skipping lines, all of those mean the same thing to the program. So this program here, when I press play, you'll see we have our 10 pixel margin around the edge, and that if I change that number to 40, we're going to get then a 40 pixel margin because the math is still checking out over here. But now watch this. If I take that same program and I basically remove the skipped lines and I remove the extra spaces that we don't need, when I press play, so here's our whole program on one line. When I press play, the exact same thing happens. All the program's looking for is a clue about where each line is meant to start and stop, are things like the semicolons and the braces, certain spaces in certain situations, like around the word int, to let it know that that's separate from our label margin. But anything else that we do about white space and indentation and spacing is just to help our ability to read it as human eyes, as programmers, for both sharing the code with others and to be able to manage our program and look at it and make sense of it, because this becomes kind of a mess pretty quickly. One thing you can do, if you ever get lost and mixed up in formatting, I don't recommend leaning on this too much. It's really useful to be in a habit of formatting your code properly as you go. But in processing, there's a powerful ability to go to Edit and Auto Format. Bam! It'll automatically straighten out your code for you in terms of indenting where appropriate inside braces and putting things on new lines after semicolons. I'm going to add a couple of spacings here that, again, are not meaningful to the program. They're just for my purposes only. Another thing we can do with programming is we can write comments. And so a comment is something where we put a // and then anything after it is ignored by the program code. So when I press play, we have the exact same functionality as we did before, no matter what I put there. Now because of that, something else we can do, let's see, put this on 2 lines to make sure you're seeing the whole deal. I can draw another rectangle and say 20, 40, 60, 80. And when I press play, so there's our first rectangle that we drew here in the code. And this other one corresponds to the second rectangle we drew. Notice that because it's happening top to bottom, the one that was drawn last overlaps the one that was drawn first. Oop, sorry about that. Now we can use a comment to tell the program to skip that code if we're testing something out and we need to know what happens if that line isn't there. I'll press play again. You'll see now it's ignoring that line. And now because this // ignores the line to the right of it, now it does matter when we break line in code. So if we do a // here, it's going to confuse the program because it only tells it to ignore this part. And this is not an appropriate way to start the next line. So when I press play, it'll give us an error. It says maybe we're missing a semicolon. It's confused about which line is supposed to be starting where. Now there's a few ways we can do that. We could add a // to both lines. And this would again skip drawing the main rectangle we did the math for. We could put all of this on one line when commenting it out, so that it all falls in the same space of what's in the comment. And there's also a way to produce a multi-line comment using an old C-style convention. Instead of // if we do /* to */, we can comment out multiple lines at a time, or even put a comment in the middle of a line, because this allows us to indicate a start and end position in a way that the // is implied on a single line. When I press play, once again, these lines are being ignored because they're commented out. This word is being ignored because it's also commented out. Now comments can be used to add notes to ourselves, to describe what we were going on, what we were thinking when we did it. Comments can be used to make notes to other programmers about how some part of the code is supposed to be used or not. It can also be a reminder to us of what a chunk is supposed to be for. And as shown there, if we're testing out functionality, we need to find out what happens if we turn off a block of code, but we don't want to delete it because we're going to need it back soon. Comments are also a handy way to do that. Now, let's move out of just doing setup calls, because that kind of gets boring pretty quick. I'm going to knock out what we have so far. Get rid of rect there as well. So again, when I press play, we have setup, which is setting the size. Let's start putting rectangle call inside draw. Now, first of all, let me point out that 30, 40, 50, 60. Remember, this is going to draw a rectangle, which is the top left corner, which is 30 pixels from the left side, 40 pixels from the top, 50 pixels wide and 60 pixels tall. And when I press play, there it is, 30 pixels from the left side, 40 from the top, 50 pixels wide, 60 pixels tall. Even though this isn't drawn, so it's happening 30 times a second, these numbers are always the same. And so nothing interesting is happening. It's not moving. It's just being drawn over itself again and again and again. What we can do is, just like width and height, remember that those variables got set for us by processing, I can use mouse X and mouse Y. You'll see how these turn into special colors for us. These are built into processing to stay up to date with the current mouse coordinate positions inside of the window. And so actually, before I demonstrate that, 30, 40, I'm going to show it first using a print line as a reminder of how we can use this to debug. So if I print line mouse X and watch the console down here, you'll see down, I guess that's going to be that direction for y'all, down there in that corner, over here, when the mouse is near the left side of the window, mouse X is 0. When it goes to the right side of the window, it becomes close to 720, which is the width of our total window. And anywhere in between, if I'm halfway, then we're going to get half of 720. If I'm a quarter, we're going to get a quarter of 720, and so on. We can do the same thing to print out mouse Y. Remember what's happening here when you see that list of numbers down there is that draw is happening many, many times a second, around 30 or so. And so while the mouse is near the top, we're going to get a 0 or something very low. We're near the bottom, we'll get up to 439, just short of that 440. If we're halfway down, we're going to get about 220. And you see how that's constantly updating. When the mouse goes outside the window, though, it keeps the previous number it was when it was in there. So if I put the mouse near the top, it's going to be a low number like 6. If I move it out, it can't see the mouse until I go back into the window, pop, and now it's back close to 440 again. And we can even combine these lines. So mouse X, I can use plus signs to what we call concatenate the strings together. I'll put a string in here with quotes, letting it know that this is not a programming symbol, this is just a word we want to pack in there with a comma and a space. Now when I press play, down there in the corner for the command console, you'll see our mouse coordinates, which will go all the way up and down. So the bottom right corner is near our window size, top left corner 0, 0. Another thing to call attention to in terms of coordinate positions is that if you're used to something like geometry or traditional math courses, you're probably used to positive y going up. So greater y values correspond to moving up away from the origin point. Due to historical legacy reasons about how memory is arranged on a computer and how computer screens were mapped to it and the motion of their rays and so on, basically the end result of that is that our y-axis is flipped, so that positive numbers, increases in y-axis, go further down on the screen, although thankfully at least increases in x go to the right, as we're used to expecting from other math. So 0, 0 is in the top left, 719, 439 is in the bottom right, and in the middle is half of 720, half of 440. Now that we've demonstrated these lines, we're going to comment them out because this slows down the program. The program actually draws things inside of our window much faster than it can print things out, especially for printing every single line every single time the screen updates. But the gist here is that instead of setting these to predefined numbers that'll never change, if we set the X position and Y position of our rectangle we're drawing to where the mouse is on the screen, then when I press play, we can now drag it around. You might be wondering, what's up with this tail? What's up with the smearing? And all that's going on there is that we're not erasing where it was before. Alright, so we could erase what's going on before. For example, if we drew a rectangle the size of our screen, remember we can use width and height as being automatically set by processing to the values that we set inside size. So this is going to draw a rectangle 0 pixels from the edge, 0 pixels from the top, 720 pixels wide, 440 pixels tall at the start of each draw call, and that's going to erase the rectangles that we previously drew based on the mouse position, which will give us a much more solid look for this moving rectangle. You see that? And this is actually a pretty traditional way for dealing with graphics buffers. This is how DOS games used to write work. It's how Windows games and DirectX used to work. It's very much a normal system. There's nothing weird going on here, including this idea of the fact there's code that happens when the program starts, and there's code that happens repeatedly in a update cycle. Same thing is going to happen for iPhone applications and so on. Now, if we want a faster way to write that, because it's so common that we want to erase the entire background, we can just call background 0. 0 here specifying a color, which we'll talk in a moment about how we can change that. And now it's going to black out that window using 0 as the color value. If we only give it a single number for background, it's going to treat it as a whiteness value from 0 to 255. So 255 will give us a bright white background. But colors are often reflected as triplets: red, green, and blue, each from a 0 to 255 scale. If you're used to web colors, you might know these as going up to OXFF, which you can actually indicate with the 0x and the hexadecimal letters. If you're not familiar with hexadecimal, don't fret, no need. All you got to know is that the color values for the red, green, and blue are on a range from 0 to 255. So if we want 0 red, maximum green, 0 blue, then when I press play, we're going to have a bright green backdrop. If I cut that 255 down to 127 and I press play, now we're looking at a darker green. If I go even further down to a quarter brightness, making that 64. Darker still. Let's say I want to add full red, no green, no blue, bright red. And if I add full green and full red together, this is an additive color scheme, so our colors are red, green, blue. Not to be confused with subtractive color scheme like painting, where it's red, yellow, and blue. But so an additive color for light, which is what a computer screen is, of course, full red and full green together produce yellow. And if we added as well full blue, red, green, and blue, all the colors of the rainbow for an additive color scheme, we get a bright white background. But so feel free to experiment there with some colors. If you go over 255, it's just going to wrap the number around. Same thing with a negative. You're welcome to experiment with it, but the numbers you're getting and the colors you're going to get won't be as meaningful as if you keep each of these numbers on a range from 0 to 255. Now again, like we showed earlier, we could do something like int box size equals, let's say, 70. And now, when I've done this, it's giving us a temporary label within this scope. So this int is only going to last between this brace, from the point at which I declare it, down until the brace is closed. A label of type integer, so a number which is going to have to be on a discrete, 57 or 58, not 57.2. A label box size. You'll see here my naming of it. I've done what's called camel casing. Camel casing is where you lowercase the first word, capitalize each consecutive word, and the idea is that it looks like the bumps on a camel's back. This is a very, very normal thing you're going to see in programming. It's the same thing we see here with mouse X and mouse Y. It's because we can't put spaces in variable names. Some people out there, you'll see things that use underscore instead. We're going to tend to reserve those for constants, which we'll get into later. But camel casing you're going to see all over the place. So box size is the name that, remember, the program itself doesn't care what we call this. We could call this whiteboard, we could call it flashlight. I'm calling it box size as a clue to us of what we mean to use the number for, setting it to 70. And then I can use that in place of the width and height of the box. In this way, I've made our code more readable. Because no longer do I have these magic 50s, 60s, and 70s floating around and having to remember what each one does. We figured it out at one time, and then that was enough. Now you'll notice, for example, here that that box, because the first two coordinates of rectangle are the top left corner of it, we have mouse X and mouse Y, so our mouse cursor is showing up in the corner of that box. What if we want to center it on the mouse? Well, one way we can center it is if instead of drawing the rectangle exactly where the mouse is, if we move that rectangle over half the box's width and up half the box's height, we're going to center it. And here's another place where we can reuse that number we have and do math in line. Slash refers to division in programming. Remember, I can go to a new line without affecting the code because it's just white space, which the program doesn't care about. So mouse X minus half the box's width divided by 2. Mouse Y minus box size divided by 2. And now we'll wind up with a box that's centered under our cursor. Like so. And again, the nice thing about doing this, putting a label on it like this, is both that this self-documents the code and that we can read each of these expressions. We might even break this down further for ourselves and say center X actually, I'm going to name it a little better. Let's say cursor X centered cursor X. There we go. Copy and paste. You want to be careful whenever you do copy and pasting. You remember to change your corresponding axes. Oops. Okay. And now again we have an even better documented, self-documented use of this code, where instead of having to have comments above that say that the first argument is the number of pixels from the edge and that we're subtracting half the value of the width of the box, we've got all this sort of wrapped up into one thought at a time. I want the box to be 70 pixels wide. I want to center the cursor on X. And never mind how this math works, I thought about it once. That was enough. Now I can just use this number. And when I draw the rectangle at centered cursor X, centered cursor Y, dimensions box size by box size, there we have the box centered. And if we want to change that 70 to something else, let's say we want a bigger cursor, 170. When I press play, all the rest of the math is still going to check out for me because we thought it out once. And it's still centered on our cursor without us having to go back and rethink or redo math, as we can trust that kind of work to the computer. Computers are great at that kind of thing. So there's some basics about setting the program size and setup, clearing the screen with a background call, and then being able to define variables in the code to help label the math that we're doing when we think through it in a way that's going to let us draw a cursor where our rectangle is. And it's possible to turn off the cursor and processing if you don't want to see that arrow there, but of course, for the sake of this video, if I did that, you wouldn't be able to see where my mouse was and prove to yourself that it's right in the center. But you look it up in the docs if you're curious. We also showed how to use a print line to be able to print out values that are debugging in memory. So remember, here if we do this, we're going to print out mouse X and mouse Y. See them down there. But we could also, just as well, use that to output our derived labels, so that now, if I position this box so the corners up here, you'll see we can get 0, 0 printing out down there. If I go all the way up to the corner, we're actually going to get negative 85 by negative 85. Because now it's printing out not where the mouse cursor is, but it's instead printing out where the corner of that box is. We can do this with any number we'd like. If we want to double check that the box size we expect it to be, we could just print that out. It doesn't have to be a live updated value. And we see pretty clearly it's always 170 as we predicted. We're going to comment that back out. Whenever you see this kind of red junk down here, by the way, I'm just going to suggest just ignore it. That's the thing that's going to happen sometimes if you're using Mac. It has to do with a version of Java and some sort of weirdness. But don't mind that. Nothing to worry about, nothing to concern yourself with. It'll show up when the program closes only. For our next example, we're going to get a ball bouncing around on the screen. First laterally, then vertically. Then we're going to account for the size of the ball. We're going to do some more exciting things to build off what we demonstrated here. Thanks so far for tuning in and following. Hopefully this has been helpful as a way to just kind of get you ramped up. And please come back, check out the next example. Thanks.